2.6, continuity, day 2. We're talking about continuity at endpoints. A function f is continuous from the left or left continuous at a. If we're coming from the left, then we can equal f of a, meaning there is a right endpoint. So coming from the left, we can have a value of f of a. F is continuous from the right or right continuous, meaning as we're approaching the endpoint from the right, and there's an actual endpoint included, and it's f of a. This also means then we can have continuity on an interval. A function is continuous on an interval I if it is continuous at all points of that interval. If the interval contains its endpoints, it means it's continuity for the interval from the right or the left endpoints. Here's examples. We have continuous where both endpoints are included. Then we have this next example where only the left endpoint is included, so then we say it's a right continuous coming from the right. The next example, only the right endpoint is included, and that means it's left continuous coming from the left. Last one, neither endpoint is included, but we do have a continuous interval. Then for this example, we have a piecewise function. We could do a quick sketch, like some kind of parabola, some kind of line. We see that it's included and not included. It is a function, passes the vertical line test, but they want to know what's the intervals for continuity. So for the interval, obviously, this is where it says it's included. So when I'm coming from the left, I have this interval of continuity here going to 0, and I'm including it. But then I'm going to be also continuous going from 0, and that's starting at this point, not including it, and going on to infinity. Since I have an endpoint only from the left, we say this one is left continuous. Okay, oops, kind of wrote it all in one. I have another example that we can do. So for example, given another piecewise function, then we can see from this one that if we were to quick sketch it, I don't even have to. I'm really looking at these two key pieces of information. And since this one is basically saying all values for x less than 1, I'm going to be coming from negative infinity to 1, but it is not included. And then from the other one, I see that the 1 is included, and it's all values greater than or equal to, so I'm going on to infinity. I'm continuing here. I have a left endpoint, so that means if I'm going to be coming from the graph in this direction, I am going to be a right continuous function. Theorem 2.13, continuity of functions with roots. So some kind of square root, nth root, something like that. This follows from 2.11 and the law 7 we had on limits. And we have here that if we're assuming the m and n are positive integers and they're simplified, it's reduced as much as we can, it says here if it is continuous for all points, if m, the denominator, the root one, is odd integer, we're continuous for all points, period, no matter what. But if m is even, this is where it becomes different. If n is even, all points are continuous at a for which the function is continuous and greater than 0. Remember, we're calculus, we're trying to keep it real, no negatives under a radical. So for example, in a, I can rewrite this function in parentheses with an exponent. So I have a rational exponent, which is that, it's not it. it is 1/2. It's the square root. It is where m is even, so I have an issue going on with this one. So in this one, I want to go ahead and say that this function has to be greater than 0. Or it could be equal to, actually. So let's say it's greater than or equal to 0. But if I want to solve for x, we have to remember properties with dealing with square roots and inequalities. So that I can do is I'm going to basically solve for x, and I'm going to drop the inequality. Just do this, -9. Move 9 over, make both sides positive. And then when I go ahead and take the square root of both sides, this is where I get an issue. Because then at this point, I've got an x where I'm going to have values greater than or less than 3 and -3. So this is where I'm talking about here, that taking the square root of an inequality becomes a compound inequality. It does, in a sense, keep that inequality where it can be less than or equal to or greater than or equal to. And then if I want to go ahead and put this in interval notation, I've got it going from -3 to 3 included. In the book, they walk through this function with a graph. We can see that it's the top half of a circle with a radius of 3. The endpoints are included in this because we can take the square root of 0. So we can have both endpoints included and having it continuous on this interval. For part B, back up here, notice it's already an irrational exponent, but it's a polynomial, and because it's an odd degree for the root, it is not any other restrictions as far as with an even root. Because we can take an odd root of a negative, it does not matter. So this one, I don't even have to do any work. It is continuous function on the whole interval. We can say from -infinity to infinity. Talking about transcendentals, remember transcendentals are functions that transcend basic algebra, like trig, exponential, logs. So basically in the book, I just wanted to tell you real quick, if we were dealing with trig functions and continuity, you have to remember what some of our basic functions were. Our sine and cosine, they graph as continuous functions. Remember, sine waves like this, and cosine wave is like this. All right? So those are continuous functions. Now the rest of the trig functions, remember there's 6, so the other 4 trig functions are continuous for their domain. Meaning, remember there are points of undefined for tangent. That is why it graphs like this. And at pi over 2 and -pi/2 were undefined. So it has some vertical asymptotes there, and same with the other 3 functions beyond that. But for its domain, it is continuous on all values of a for its domain. So domains could be from positive pi over or -pi/2, or multiples, or remember it was for all values except odd integers, odd n times pi. There's another way of notating it that I'll get back to later. The other one is exponential functions, and we're going to just assume they're always, you just have to go ahead and look at each individual function. So then that leads us to theorem 2.14, continuity of inverse functions. If a continuous function f has an inverse on this interval, then its inverse has it. It also is continuous on this interval consisting of points where x is in the interval. 2.15, continuity of transcendental functions. This basically goes ahead and lists that all these functions are continuous at all points of their domains. Remember, not all of them have all real domains, though. You have to check. So we have the trig functions, the inverse trig functions, the exponential, and the logarithmic functions. The last thing I want to talk about is with dealing with these. As long as it's in the domain, you can do direct substitution. So last examples I have here. Evaluate the following limits after determining the continuity of the functions involved. So for A, remember there should not be any issues because we're dealing with cosine, but we have an issue in the denominator. So coming back to A, we said we had an issue with the denominator. And where would this happen? We can have cosine x. If we add 1 to both sides, there would be an issue when cosine of x equals 1. And that happens all in multiples of 2 pi. So if that's the case, we can't have any multiples of 2 pi as being points of discontinuity. So we can go ahead, though, if we notice A factors, so we can go ahead and do our factoring of the top. It's a difference of 2 squares. So we have cosine x minus 1 and cosine x plus 1 over cosine x minus 1. These reduce. And at this point, I have no issue where I can do direct substitution. So I have cosine of 0 plus 1, and cosine of 0 is 1. 1 plus 1 is 2. So it does have a limit, and we can find it as long as we talked about determining continuity of the function first. So for B, the book goes through a big explanation about the fourth root of the natural log. Remember, though, with natural logs, you have to make sure it makes sense and its domain restrictions are, it has to be greater than 0. If we were to take the e of both sides of this equation, we get x is greater than 1. And if that's the case, then we can go ahead and continue looking at this. We're saying then the fourth root of it has to be greater than 1. So then at that point, I can say, okay, I'm continuous for that part of this function from 1 to positive infinity. Can I include 1? I think I can. Makes sense, right? I can have the square root of 1 under the fourth root of 1, and can the natural log of x be 1? And it can. So I can go ahead and definitely say I can include this 1 into this point. So if we say this is right continuous at this one, with the left endpoint included. And then I have to look at the tangent inverse function. And if this one is the case, remember the tangent inverse, this one graphs like this. And there doesn't seem to be any issues. So it looks like I'm continuous from negative infinity to infinity. So that if that's the case, putting both of these properties together, they have to both work together when I take the limit of this function. And I'll write it again. As x is approaching 1 from both sides of this function. And remember our sum property, or law of limits, so that I could break that apart. And then we can see that we are only dealing with a continuity issue from 1 to infinity. But I can go ahead, if I take the limit using my sum property of this first one plus the limit as x is approaching 1 of the second one, I can evaluate it. So if we do that, though, I can see that we're doing two-sided. These do not, I can't do that when I'm dealing with this and this. at this point, I say the limits do not exist. I can't do this point of interval of continuity for both functions. Intermediate value theorem. This graph, there's two graphs, but it's just saying the intermediate value theorem is saying there's got to be at least one point in an interval where a number c such that it's the limit is between the endpoints. Makes sense. This has to have at least one value of c with an actual limit. It doesn't mean there can't be more. In this case, it turned out there was 3 of them. But the theorem says, the intermediate value theorem says there has to be at least one where there's a value between the endpoints. So when we go ahead and say this theorem, intermediate value theorem, suppose f is continuous on the interval from a to b, and L is a number strictly between f of a and f of b. This means we have to have a closed interval. Then there exists at least one number c in the open interval, satisfying that the f of c is equal to a limit. So we have open and a closed interval that I'm dealing with. Notice here, there is no c that's an element of a to b such that f of c equals L in this non-continuous case. This is non-continuous. I am not continuous on an interval. I would have to even break it down into this, and then I'm not sure if I can prove that by the intermediate value using this first piece from here to here. The only one that's a closed interval would be from this point to that point, and then maybe I could use an intermediate value theorem. But as it stands in the given situation here, there is no closed interval, no c that will satisfy this. So then let's go ahead and use an interest rate problem from our book. Suppose you invest $1,000 in a special 5-year savings account with a fixed annual interest rate R and monthly compounding. The amount of money A in the account after 5 years or 60 months is given this equation, A of R, compound interest formula. Your goal is to have at least $14,000 in the account after 5 years. That's at 60. Use the intermediate value theorem to show that there is a value of R in this open interval, 0 to 0.08, that is an interest rate between 0 and 8%, for which we can find this amount of money. Basically, though, I have to use the closed interval from 0 to 0.08 in order to find the intermediate value theorem. So I'm going to take those values for A and B and plug them into my equation. A of 0, which should be $1,000, and A of 0.08%, plugging that into my formula. And that one ends up being about 1489.85. So this is the amount of money that I have for my endpoints. And then by the intermediate value theorem, it's definitely going to have some interest rate in between this on this open interval. So the open interval from 0 to 0.08 interest rate. There will be some value at some rate in 5 years that I will make at least $1,400. So that proves that. But by B, it's asking for me to use a graphing illustration to explain A. They do this in the book. They graph the function, and it looks something like this. So here's, oops, let's do this A or 0 here. And then let's do 0.08% for B. So in between here, between 0 and the 0.808 is some percentage rate. Somewhere in here by the intermediate value theorem between here and here will get us the right amount of money. So here we said is our $1,000. Here when we did this endpoint, we said it was 1489. 89.85. So we would have to calculate it, and then you could use a chart, or we can plug this equation into the calculator and graph it and use a table. And it does say, okay, there is a value here. It turns out to be 0.0675. That does get us the right amount out, the $1,400. So this is the one that we were looking for, and it is proved by the intermediate value theorem.